Hi, everyone. I hope you're doing well. This is a short video about absolute value functions. We'll also talk a little bit about power functions and polynomials. So a minor logistics note, as you can see from the numbers here, we are skipping section 2.4 in the book, which is about fitting linear functions to data. That's really a topic from statistics, and it's an important one, but we will skip it in the name of consistency. Okay, so absolute value, I expect you've all seen absolute value before, but nonetheless, we use these vertical bars to symbolize absolute value. So when we put something between those vertical bars, that means the absolute value of that thing. And the way you take the absolute value of a number is pretty straightforward. If the number is positive or zero, here we go, you just leave it alone. You don't do anything. There we go. And if the number is negative, most people think of this as dropping the negative sign, which is true. We can express that by adding another negative sign, right? Because minus becomes plus. So for example, the absolute value of a positive number like 4 is just a number, and the absolute value of a negative number, well, the negative sign goes away. And the sort of reason for this function is measuring distance from 0. In fact, that's a good way to think about the absolute value function, and distance can't be negative, right? A negative distance doesn't really make any sense. So for a negative number, the number -8 is 8 units away from 0. It's just to the left instead of to the right, as with a positive number. It's also worth noting that if you take the absolute value of the difference between two numbers, you're measuring the distance between the two of them. And when I say distance, I mean on the number line, right? That's where we sort of picture single numbers. We picture pairs in the plane. Distance in the plane is a little more complicated. We'll come to that a little later on, of course. So for example, I think this next thing is an example. If I want the distance from -5 to 7, you can probably, if you just think about this, -5 is 5 units to the left, 7 is 7 units to the right, so they're 12 units apart. And indeed, if you take the absolute value of their difference, -5 minus 7 is -12, absolute value of -12 is +12, so you get the right answer. It doesn't matter what order you subtract here. If you had subtracted in the reverse order, you'd still get the same distance of 12. So definitely something worth remembering. And in particular, absolute value allows us to express some sets on the number line nicely, right? So this set, which looks a little complicated, if we think of the absolute value of a difference as distance, what this means is the set of all x such that the distance from x to 5 is less than 3. So what numbers are less than 3 units away from 5? Well, you can go as far as 2 to the left and as far as 8 to the right. So this is just the interval from 2 to 8. And on a number line, whoops, that's not the cell I wanted. On a number line, that of course just looks like this. And we've graphed intervals before, so there's nothing terribly new about this, but notice that the number 5 is right in the center of this interval, and I go 3 units to the left and then 3 units to the right to get the set of all points that are distance less than 3 from 5. Okay, the absolute value function has a graph that looks like this. So this is the graph of y equals the absolute value of x. It's one of the toolkit functions, so this is something you should already be familiar with. And of course, we can shift this in all sorts of ways using our shifts and stretches from earlier in chapter 1. So here are a few examples. And again, nothing really new here. We talked about shifting and stretching before. If I do something like this orange thing, the second thing here where the cursor is, I'm adding 6 outside the function. So that just takes the blue V and shifts it up 6 to the orange curve. And then the bottom one here, I'm subtracting 3 inside the function. So that's a rightward shift of 3 units. And you can see the green V is shifted to the right by 3. Because of the shape, it's relatively easy to keep track of the shift. We just kind of move the bottom of the V appropriately. And conceivably, there could be stretches and reflections, right? We can modify the absolute value function that way as well, right? If I multiply by 2 outside the function, I'm stretching vertically by a factor of 2. And notice how the orange curve does that. And notice how where the function hits the x-axis, it's pinned down in the stretch, right? So when you stretch, you don't move points that are on the x-axis, you just stretch the other points. So see how this is different than a shift. It's not the whole curve picked up and moved, it's stretched away from the axis. And then something like this, so the minus sign here reflects vertically, and then I add 4, so I shift up by 4 units and I get this green curve, right? So when I put the minus sign in, I flip the V upside down, and then adding 4 moves it up. Okay, so a quick exercise, and this comes from the notes and exercises here, right? I have this function and I copied it over in the other document. I want to find the y-intercept, the corner point, right? Absolute value functions we've seen from these graphs have corner points, and let's go ahead and draw the graph as well. Okay, so to find the y-intercept of any function, all I have to do is evaluate f of 0, right? The y-intercept is always the point on the y-axis when the input is 0. So that's just a matter of plugging in, and I do some math and come out with a y-intercept here of 22. As far as the corner point, the key is understanding the shifting going on here, and then just kind of following how the corner point moves, right? So this is going to shift to the right by 6 units. The stretch won't affect the corner, right? Because the corner is pinned down in the stretch. And then I go up by 10 units. The original corner, if I go back to the original graph, is 0, 0. It's the origin. So if I shift to the right 6 and up 10, that point is going to move to the point 6, 10, right? So this is my new corner point 6, 10. And we've now talked about all the different transformations going on here. So here's what the graph looks like, right? You can see the graph has been shifted over. So the corner, which used to be down here at the origin, is now at 610. And there's a vertical stretch here that is that's difficult to see without the graph of the original. Okay, let's talk a little bit about solving equations and inequalities with absolute value. First, if I ask the question, where is the absolute value of a number equal to 3? Well, there's only 2 numbers that satisfy that, right? Positive 3 over here on the right and negative 3 over here on the left. And you can change this 3 to some other number, and it's not going to change much, right? Where is the absolute value equal to 4? 4 and negative 4. Where is it equal to 5? 5 and negative 5, and so forth. This is helpful even in solving more complicated absolute value equations like this one here. I'm going to do this in a 2-step process. The first thing I'm going to do is isolate the absolute value, right? So I'm going to do some algebra to isolate the absolute value, and here's what that algebra looks like. So I start with the original, I subtract 4 from both sides, and that gets me here. And when I say isolate the absolute value, I just mean make one side of the equation just the absolute value with nothing else going on. And now once I do that, I have an equation that says the absolute value of something is equal to 11, which means that something has to be either positive 11 or negative 11, right? So this is a fancy way to say that. The absolute value of a equals y means either a is y or a is minus y. More concretely, in our example, the 2x minus 1 is either equal to 11 or it's equal to negative 11. And I get 2 equations here that don't have any absolute values in them. So those are pretty straightforward to solve. Whoops. I just have to add 1 to both sides and then divide by 2. Right in the first equation, I add 1, I get 2x equals 12. In the second, 2x equals negative 10, divide by 2. And I get 2 solutions to the equation, right? Equations can have 1 solution, no solutions, 2 solutions, 17 solutions. So there's nothing sort of awkward about this, right? So the solution to this equation is there's 2 solutions, x equals 6 and x equals negative 5. Okay, what about inequalities involving absolute value? If I ask the question, where is the absolute value less than 3? So not equal to 3, but less than 3. Well, since absolute value is distance from 0, this means your distance from 0 is less than 3, which means you have to be between negative 3 and positive 3. And if I change the question to less than or equal to instead of less than, I don't change a lot. The only thing that changes is that the endpoints are included if it's an or equal to, and they're not included if it's a strict inequality, just a less than. Okay, so how does that help us when it comes to a more complicated absolute value inequality like this one? Well, again, step one is going to be to isolate the absolute value. That's what I just said. Yes, step one is to isolate the absolute value. So here, to do that, I just have to divide both sides by 3, rather. Times is a little confusing. Let's do that. Right, so when I divide both sides by 3, I get this inequality. 48 divided by 3 is 16. And again, I have on one side of the inequality only the absolute value with nothing else, right? So that's the first thing that I want to do. And now I'll just use what we did up here to interpret this. If something's absolute value is less than or equal to 16, it means that that thing is between negative 16 and positive 16. So that means in this case, that x plus 8 is between negative 16 and positive 16. Notice how we can write between using a string of inequalities, right? So if you are between negative 16 and positive 16, it means you're greater than or equal to negative 16 and less than or equal to positive 16. And we can write that very compactly like this. And now I can solve for x, right? I just subtract 8. And when you do that in a string of inequalities like this, you do it in each of the 3 slots. So one slot's over here, one slot's in the middle, and the third slot is on the right. And when I subtract 8 in every slot, I get negative 24 on the left, the 8 cancels in the middle, and I get an 8 on the right. And now I get the solution to the inequality, right? The solution here is that x has to be between negative 24 and positive 8. And that, of course, is an interval. It's the closed interval because the endpoints are included from negative 24 to 8. Okay, what about asking this question? Where is the absolute value greater than 2, right? So we have asked, where is absolute value equal to? Where is it less than? Now, where is it greater than is the other possibility. Well, if your absolute value is greater than 2, it means you're more than 2 units away from 0. So it means you're either out here on the right or you're out here on the left. And if we change it to greater than or equal to 2 instead of just greater than, that doesn't change a lot. It only changes what happens at these endpoints, right? The endpoints are not included. Notice the open circles if it's a strict greater than inequality, and they are included, the closed circles you can see here, if it is an or equal to, a loose inequality. Okay, so this can help us solve inequalities like this one. Anytime I have an absolute value inequality like this, my first step is going to be to isolate the absolute value. So you might look at this and say, wait a minute, is this like a less than or a greater than? Just isolate the absolute value and then it will be clear. So yes, good idea. Isolate the absolute value. So first I'm going to add 25 to both sides. Right, so when I add 25 to both sides of the inequality, I get 126 and it cancels on the right. And I have succeeded in getting the absolute value all by itself on one side. This is an absolute value being greater than something, right? So it is this third category. And if your absolute value is greater than 126, it means that you are either greater than 126 or less than negative 126, right? And so whatever is in the absolute value is either greater than 126 or less than negative 126. Notice that we don't use a string inequality here when it's a greater than. That's in the less than case. This is an or, not an and. Again, I get 2 inequalities that don't have any absolute values in them. So I can solve those using ordinary algebra. I just subtract 10 from both sides, right? So over here, I get 3x greater than 116. And then 3x less than negative 136, and then finally divide by 3. And when I divide both sides by 3, I get x is greater than 38.7 or x is less than 45.3. And we can express that in terms of intervals. Remember how you put 2 intervals together using that union symbol as the interval from negative infinity to negative 45.3 unioned with the interval from 38.7 to infinity. And this is good practice. I mean, if you leave your solution like this, I would say you're 95+% of the way there, but it's nice to just clean it up a little bit. Okay, there are a bunch of examples of this kind of thing in the notes and exercises. I'm not going to go through these in the video, but I will open these solutions so that they'll be there in the notes for you to look at. And of course, in the text, there's lots of examples as well. So practice, practice, practice is the way to get good at solving those equations and inequalities. Okay, moving into chapter 3. And the first thing to talk about here are power functions. And you can see, by the way, that what we've been doing of late is kind of touring different families of functions. We talked about linear functions, we talked about absolute value functions. Now we'll talk about power functions and polynomial functions. This is a class all about functions, right? So always we have an input and an output. So a power function is a function that has this very special form. F of x is x raised to a power, where the power is just some number. Okay, so this looks a little different than the class of linear functions, right? Linear functions were functions of the form f of x equals mx plus b. We'll consider two important special cases first, depending on the power of p. One where that's an odd number, 1, 3, 5, 7, et cetera, and one where it's an even number, 2, 4, 6, 8, 10, and so forth. So let's take, for example, p equals 3, right? So if the power is 3, the function is f of x equals x cubed. And you'll recall that this is repeated multiplication, right? 2 to the third power is 2 times 2 times 2 equals 8. So just a reminder of, you know, how integer powers work at any rate. So we know what power functions are doing, at least in some important special cases. So here are some graphs. And you can see they're color coded, right? The blue one is x cubed, and the orange x to the fifth, the green x to the seventh. And I'm just kind of walking up odd powers starting from 3. And you can see kind of what happens is the curves move up on the right and they move down on the left, right? So they kind of become like a steeper and steeper S. They also get flatter in the middle. So it's worth being acquainted with this general phenomenon. We are going to be interested, among other things, one of the things we'll be interested in for power functions and polynomials is something called their end behavior. And the end behavior is what happens to the outputs as the inputs go either to positive infinity or to negative infinity. It's called end behavior because we're asking what happens to the function as the input heads toward the end of the number line. And there's two ends, of course, you can go to the right or to the left. So we have sort of two end behavior questions about really any function, but especially in this case, we're interested in it, right? So this is just reiterating what I just said. The behavior of the outputs as the inputs move towards the end of the input line is called its end behavior. So notice as x goes to positive infinity, if we look back up at the graph, that means we're moving to the right, right? So x going to positive infinity means the inputs are going off to the right. And what we're asking is on these curves, where are the y values going as the inputs go to the right? And the answer is the y values are going up, right? They're going up, you know, more quickly in some cases, but they're all going up. And in fact, the outputs all go to positive infinity. On the other hand, if the inputs go to minus infinity, so this is the second case, so this means I'm going down to the left, right? The inputs are going this way. What happens to the outputs? They go down, they go down, they go down. They are going to negative infinity. All right, let's look at the even power case. I think we're going to start right in with a picture. Again, so here are the first few even powers, 2, 4, 6. Y equals x squared is a toolkit function, so you should know what that one looks like, right? It's that the u that kind of sits at the origin. Here, because the other ones are included, this u is really, really flat, and that's because of the scale, right? You can see the y-axis has a really big scale. What happens as I turn up the power here is, again, the curves kind of go up on either side, right? On the right and on the left. So these curves become sort of a steeper and steeper u as you increase the even power. Okay, so the end behavior here is going to look like this, right? As x goes to infinity, so we're going out to the right. What's happening to the outputs? These curves are all going up to positive infinity. On the other hand, as you go to the left, again, they're all going up. Notice that this is different from the odd power case where the curves were going down. And so in both directions, the output goes to infinity as the input goes to either infinity or negative infinity. Notice that we'll never talk about something equaling infinity. Infinity is not a number. Rather, this describes a behavior. It says that the output's getting bigger and bigger and bigger without bound as the input grows towards infinity. You can see this a little more precisely on this little gadget. So here I can control the power. This is y equals x cubed. Oh, you can see over here, there's an indication of what power we're looking at. And if I move my input, so the red dot is sort of what I want to do when I'm interested in end behavior is sort of move the red dot to the right and ask what happens to the y values. And you can see the y values getting bigger and bigger as the input goes to the right. On the other hand, if I move the input to the left, right, the y values get smaller and smaller. So they're going to negative infinity as the input goes to the left and positive infinity as the input goes to the right. Okay, let's talk a little bit about polynomials, and we probably won't get all the way through this, and we'll pick it up in the next video. First of all, some terminology. A term is a power function multiplied by a number. And we should say, let me add something here, with a positive integer power. Right, so we said at the beginning that p is any number, so conceivably p could be like pi or 4.2 or something like that, and those are all legitimate power functions. But for polynomials, we're going to restrict ourselves to positive integers, so that means counting numbers like 1, 2, 3, 4, no fractions or decimals or pies or anything like that. So here are some terms. Right, here's an example of a term. I take a number called the coefficient and I multiply it by a power function. So 3 times x squared, 14 times x to the 9th, 6.3 times x to the 12th. The coefficient could be anything. It could be a decimal, or it could be a negative number like this, minus 5x cubed. Something like this, minus x, that's actually a linear function. It's also a power function. Our function families can overlap a little bit because x is x to the 1. We'll also count constants as power functions. So let's change positive here to non-negative. Right, because x to the 0 is 1. So anything times x to the 0 is just itself. So I can think about -8 as a term, even though that's an odd way to write it, admittedly. Okay, so that describes what terms are. A polynomial is just a sum of a bunch of terms. So I just add up, and I can add up as many terms as I want. Right, so here is, whoops. Here's a polynomial that has 3 terms added together, right? The terms 3x squared, 4x to the 7th, and minus x. Here's a polynomial that has 2 terms. Here's another polynomial with 3 terms, right? You could have a polynomial with 8 terms or 10 terms, or even just a single term qualifies as a polynomial. Okay. A little more terminology. The highest power in a polynomial is its degree. So if I look at this first polynomial, the degree of that polynomial is 7. Notice it's not the term that comes first, it's the term with the highest power of x. The degree of this polynomial is 72, highest power of x, and the degree of this polynomial is 4, highest power of x. Alrighty. And the term that contains that highest power is called the leading term. So again, the leading term is not necessarily the term that's written first. It's the term with the highest power of x. Often when we write polynomials, we will write the leading term first and write the powers in descending order. It's a little easier to look at this that way. But for this polynomial, and actually I think I have a table here that has all this information. So let's just open this up. And the coefficient of the leading term is the leading coefficient. So let's look at our polynomials. And so these 3 are the same polynomials that I mentioned up here in this example. So for this first one, the leading term is the term with the highest power of x, right? That's the 4x to the 7th. The leading coefficient is the 4, that's the coefficient in the leading term, and the degree is the power of x in the leading term, the 7. For this guy, the leading term is the negative 9x to the 72, right? The 72 is the highest power of x, so that's the degree, and negative 9 is the leading coefficient. And finally here, 10x to the 4th is the leading term, 10 is the leading coefficient, and 4 is the degree. It's the power of x in that leading coefficient. Okay, a word about end behavior of polynomials, and then I think we'll call it enough for this video. The key fact about a polynomial is end behavior is dictated entirely by the leading term. So there's more to the polynomial than that, but if all we're interested in is an end behavior, then we can ignore everything except the leading term. A positive coefficient leaves the end behavior of a power function unchanged. Now, why am I saying this? Because if you look at these leading terms, here's a leading term, here's a leading term, here's another leading term, they all look like number times a power function. And we know about power function end behavior, right? Depending on whether the power is even or odd, we just talked about that. So the question is, what does the coefficient do to end behavior? And the answer is, if the coefficient is positive, it doesn't do anything. It leaves the end behavior unchanged. And if the coefficient is negative, it's going to reverse the end behavior. Okay, so for example, in looking at this leading term, 4x to the 7th, now that's an odd power function, right? So that's going to have this kind of shape, right? Where it's going to go up to the right and down to the left. The coefficient is positive, so that's not going to change anything. So now I know the end behavior of this polynomial. And I think that's probably the next example here. Let's see. No, I do some other ones down here. So let's finish our thought and then we'll do these examples. So this polynomial goes to infinity as x goes to infinity, and it goes to minus infinity as x goes to minus infinity, because it behaves like an odd power function. Right here, I have a term, again, it's an odd power. The positive coefficient won't change anything. So as x goes to infinity, all I have to think about here is what happens to x to the 5th, and the answer is it goes to infinity. As x goes to minus infinity, again, the positive coefficient 4 won't change anything. And I know that for an odd power, it's going to go to negative infinity as x goes to the left. So the whole term here, in fact, goes to negative infinity. A few more examples. So here, I have an odd power function. Okay, so as x goes to infinity, that would go to infinity. But I have a negative coefficient that's going to reverse that. And so instead of going to infinity, it will go to negative infinity. As x goes to negative infinity, so I'm looking at the same term here, and again, I start with the power function. All right, it's an odd power function, so as the input goes to the left to negative infinity, the outputs go down to negative infinity, but the minus 9 is going to reverse that, and so this term goes to positive infinity. All right, how about this term? Start with the power function. So that's an even power. So it has a U shape, which means it goes to infinity in both directions. The positive coefficient isn't going to change that. So this output goes to infinity. And in fact, it doesn't matter here whether x goes to plus or minus infinity. It does matter in general, just not in this example, right? In either case, x goes to minus infinity or plus infinity. These terms go to plus infinity. All right, I think we have one more example here. Again, I have an even power function, so that's going to have a U shape and go to infinity in both directions. But the minus coefficient is going to reverse that and make this go to negative infinity. And that will be the case in, again, both directions. Okay, so if you're faced with a polynomial like this, and the question is, what's the end behavior of this polynomial? Well, first thing is, I'm just going to focus on the leading term, which is that guy, right? That has the highest power of x. This is an odd power function, right? So it has that kind of S curve. Let's open this up, right? So the function behaves like its leading term. And as x goes to infinity, this odd power function would go to infinity. The positive coefficient won't change that. So the function is going to go to infinity as well. As x goes to minus infinity, let's do that example as well. So let's put a minus in here and see what happens. Still behaves like its leading coefficient, but this time the power function would go to negative infinity, right? Because x is going to the left. Positive coefficient won't change that, so the polynomial goes to minus infinity too. Okay, all right, let's leave polynomial intercepts and quadratic functions for the next video. Take good care of yourselves, folks.